Hey folks, this is Jim here at Science Talk. And this is an abstract from a paper that was just published near the end of September 2022 in Journal of Geophysical Research Oceans. And it's kind of an interesting one here. Um, it presents uh, another possible physical mechanism that we need to consider when we examine uh, what takes place physically in the North Atlantic in terms of mixing, what it might mean for uh, AMOC and other processes happening in the North Atlantic. And the article is called The Slantwise Convection in the Irminger Sea. Now, for those of you who don't know what the Irminger Sea is, fear not. This is, I'm sure you recognize, this is Greenland. This is the Irminger Sea, right here. Iceland is off this way. This is the Irminger Sea. There's also the Irminger Current, which is basically a branch off the Northwood Drift, which is, of course, what the Gulf Stream becomes as it gets more north. And the Irminger Current, which is warm and salty water, helps form part of what's called the subpolar gyra. There is a little subpolar gyra in the far reaches of the North Atlantic. So this kind of gives you an idea where they're talking about as we go through the uh, abstract here. Okay, so that silly thing. The subpolar North Atlantic is the site of significant carbon dioxide, oxygen, and heat exchange with the atmosphere. Yeah. This exchange, which regulates transient climate change and prevents large scale hypoxia throughout the North Atlantic, is thought to be mediated by vertical mixing in the ocean surface mix layer. Hypoxia just means low oxygen levels. So if you have mixing, you're basically helping to increase oxygen levels, which is, of course, useful for organisms. And vertical, we have in the ocean, the upper layer is usually referred to as a mixed layer because you have wind action blowing over the surface. The wind action induces activities in the water column, and that you have a mixed layer, which is basically, it is as deep as the effects are felt. So wind blows over, it's pushing on the water, there's some vertical mixing, and how deep it goes really is a function of how strong the winds are. Here we present observational evidence that waters deeper than the conventionally defined mixed layer, in other words, below what we call the mixed surface layer, are affected directly by atmospheric forcing in this region. In other words, they're saying that the wind forcing may be more pronounced than previously thought. When northern winds blow along the Irminger Sea's western boundary current, I just showed you that right off, Greenland there, the Ekman response pushes denser water over lighter water. Now, if you push denser water over lighter water, you are really going to be creating a bunch of mixing because that denser water wants to do what? It wants to sink. Then, as it sinks, it's going to do what? It's going to go right through the lighter water, and the lighter water at the same time wants to float upwards, right? Buoyancy wants to move upward. So you're going to get a whole bunch of mixing, vertical mixing all over the place, and when you throw in some current, there'll be some horizontal mixing, and that gets to this point here. So the Ekman response pushes denser water over lighter water, potentially triggering slantwise convection. In other words, instead of being completely vertical, it's off at an angle, kind of splitting the difference between horizontal movement and vertical movement. We estimated that this down front wind forcing, now this is a really important statement, is 4 times stronger than air sea heat flux buoyancy forcing and can mix waters to several times the conventionally mixed layer depth. All right, let's look at that. For this mixing, this wind forcing, they estimated to be 4 times stronger than air sea heat flux buoyancy forcing. So in other words, you have differences in temperature in the water. Water wants to find a way to mediate the differing temperatures. You're going to have a diffusion to try and have an even spread of temperature. That diffusion is your flux. And here to talk about air sea heat flux, so that means fluxing from the air to the sea to the air. Okay, you have a diffusivity. I just discussed in a recent video what diffusivity is all about. Might want to check out that video there. So what they're saying is that the wind blowing is 4 times stronger than simple heat flux diffusivity. And thus, as a result of that being a stronger forcing than the heat flux diffusion forcing, it can mix waters to several times the conventionally defined mixed layer depth. In other words, the effects are felt deeper. Slantwise convection is not included in most large-scale ocean models, which likely limits their ability to accurately represent subpolar water mass transformations and deep ocean ventilation. So in other words, what they're saying is this is a mechanism that's really not included in the models, and it should be, because that might help fill in some unknown information and help improve the accuracy of these models, and which would improve our understanding. Okay, let's look at the key points here. And before I go further, if you got this slantwise convection, and the effects are deeper than before, and you're mixing down, whatever it is you're mixing down, heat, CO2, oxygen, so on, that will impact deep ocean ventilation or overturn. That's what ventilation of the ocean means, kind of overturning. You're mixing it top to bottom. All right? That's what it means. So this could be an important aspect, an important physical mechanism. Okay, downfront wind buoyancy forcing is stronger than heat loss buoyancy forcing in the western Irminger Sea. We observe a subsurface ocean response to downfront winds consistent with slantwise convection. Slantwise convection may mix waters to several times the conventionally defined mixed layer depth in this region. Plain language summary. Deep ocean is an important part of the climate system as it stores CO2, carbon dioxide, and heat away from the atmosphere for hundreds of thousands of years. And of course, and if the deep water formation is slowing, well, that sequestration is also going to be slow. The transfer of properties between the atmosphere and deep ocean is broadly thought to occur in mixed layers formed by cooling at high latitudes. In other words, this is a bit of a quick review. The ocean, the warm currents move northward, gives off its heat. It's very salty. Now it becomes very cold. It sinks, vertically. And then we get the deep water formation, and that sequesters heat and CO2, and we get the conveyor belt, and off we go. Here we suggest that winds blowing in the same direction as ocean currents can trigger slantwise convection. And that's an important point here. The winds are blowing in the same direction. So you got a current flowing this way, and you got a wind blowing right behind it, instead of at an angle or against or what have you. It just helps push it down. And then, so it can trigger the slantwise convection, which causes properties to mix to several times the conventionally defined mixed layer depth. We hypothesize that slantwise convection is active in the Irminger Sea as well as western boundary currents across the subpolar North Atlantic region, representing slantwise convection. Ocean and climate models may be an important component of reproducing pathways into the deep ocean. Now, when they talk about boundary currents in the subpolar, okay, we're not talking about the main gyres in the Atlantic Ocean. That's not subpolar. We're talking about the subpolar gyre that occurs far north in the Atlantic. And that's, by the way, that subpolar gyre is actually cyclonic, so it flows in a counterclockwise manner. The major gyres in the ocean are anticyclonic, flowing clockwise manner. So the subpolar gyre in the North Atlantic is cyclonic, counterclockwise, which helps bring nutrients up to the photic zone. One of the reasons why it's a productive area. Just like the Gulf of Alaska has a cyclonic, counterclockwise gyre. And the Gulf of Alaska is a very highly productive region of the ocean. So I find this interesting that, here's another possible physical mechanism that should be considered. More work needs to be done to ascertain more details about it, what the actual contributions are. But if their hypothesis bears out, this is an important physical mechanism. And once we have a better understanding of the physical properties and some values, some hard data, they can then start including that mechanism into the models, which would improve our understanding of basically circulation, deep water formation, ventilation, and other physical processes from the surface down to depth. So interesting development, something I wanted to bring to your attention here. If you value and find my work to be interesting here, please subscribe to my channel. Please share my videos. And please click the like button. Doing so helps improve the algorithms, and which hopefully will increase my subscriber numbers, as well as make my channel more visible to more people. If you are not already a patron of mine, I hope you will consider becoming one. Details are in the subscription box below. Thank you for your support, and until the next time.